Hello dear students, in the previous session we were discussing about Riemann-Stieltjes integration. We have seen the definition and existence of Riemann-Stieltjes integration and we solved one problem on that topic, right? So I have given one problem as an assignment. Hope you have all done that. The next problem is f of x is equal to x and alpha x, which is nothing but your monotonically increasing function, is nothing but x. If I have denoted x in this bracket, means this is nothing but greatest integer function, okay, within the interval, that is closed interval 0, 3. So greatest integer function is actually a mapping from your real numbers to integers. That means I can define that as greatest integer function, and here the domain is R and the range is integers. So as we know, if I consider just a trigonometric function like sin x or cos x, there the domain will be R and the range will be -1 to 1, and in that interval you will get a graph in this way, right? So when it comes to a greatest integer function, the graph you will be getting will be different. That is 1 2 3. Here I will denote -1 -2 -3. This greatest integer function is monotonically increasing function and you will be getting a graph in this way. Similarly for negative, so what happens here is, if the value of your x, that is greatest integer value, is 0.9, that is somewhere here, we will consider the integer which is the greatest integer before this. That means here the greatest integer is 0, so 0.9 value will become 0. Similarly, if I have 1.5, 1.5 will be somewhere here. You will consider the greatest integer before this point, that is not x, that is excluding this point, so it will be 1. So my 1.5 value will be 1. Similarly, if I consider the negative axis, if I choose -2.4, 2.4 will be somewhere here. You will select the point which is left side to that, that is -3. So value of -2.4 is -3 when this -2.4 is a greatest integer function. Similarly, if I want to find out -0.5, the value of -0.5 will be -1. This is how you will get the value in the case of greatest integer function. You can observe with each and every intervals you will be getting different functions, that is your function is not continuous here, right? So whatever may be the interval, we will divide the interval from 0 to 1, 1 to 2 and 2 to 3. Okay, so first what I have to do in order to solve this is, I have to divide my intervals as 0 to 1, 1 to 2, 2 to 3. In this interval you will get from 0 to 1 the nature of the graph will be same, from 1 to 2 the nature of the graph will be same, and from 2 to 3 the nature will be same. If this is a continuous function, then you need not to divide your interval. Since the function is not continuous, or you can say that it is a step function, we will divide our intervals. Okay, so now I have to find out LP of alpha separately for these 3 intervals, then I should add. In the definition and existence we have seen for partition P1, for partition P2 and for partition P3, like this, right? This is what we will implement here. So now I will find out the values separately for these three, and then I will combine all threes in order to find L of P comma F comma alpha and U of P comma F comma alpha. Okay, so now my partition, overall partition P will be 0 comma 1 by n, 2 by n, so on up to I minus 1 by n, I by n, so on up to 1, then 1 plus 1 by n, 1 plus 2 by n, so on, comma 1 plus I minus 1 by n, 1 plus I by n, so on up to 2, then 2 plus 1 by n, 2 plus 2 by n, so on up to 2 plus I minus 1 by n, 2 plus I by n, and the last one is 3. So from here to here the partition is P1. Again from here to here the partition is P2. From here to here the partition is P3. Alright, so now we can find out infimum and supremum within the interval xi minus 1 comma xi. That is nothing but mi, which is f of I minus 1. This is for the interval 0 comma 1. Okay, so mi is nothing but f I minus 1. Sorry, it is I minus 1 by n. So you will be getting, since f of x is just x, it is I minus 1 by n itself. Similarly, what is capital Mi? It is f of I by n. So you will be getting I by n itself. Now I have to find out delta alpha I, that is nothing but alpha of xi minus alpha of xi minus 1. Since alpha x is greatest integer function, I cannot just write in that way. So what I will do is, I will just rewrite this in my summation part, then I will expand my summation. Okay. Now how can you write your L of P comma F comma alpha? This is nothing but summation I is equal to 1 to n mi into delta I. I will just substitute the values. This is I minus 1 by n into alpha of xi minus alpha of xi minus 1. Right? So expand the summation now. You will be getting, when I is equal to 1, this term will be 0. So 0 into anything is 0, plus 2 minus 1 is 1 by n into alpha of x1 minus alpha of x0, plus it will be continuing, that is 2 by n into alpha of x2 minus alpha of x1, plus so on up to n minus 1 by n into alpha of xn minus alpha of xn minus 1. So what is alpha of x1? If alpha of x is equal to x, then alpha of x1 will be x1, right? So now this is nothing but 1 by n into x1 minus x0 plus 2 by n into x2 minus x1 plus so on up to n minus 1 by n into xn minus xn minus 1. This is what you will get. So now we have to substitute the values for x1, x0, x2, xn and xn minus 1. How can I substitute the value? From the definition of greatest integer function, we know that if x value is till 0.9, it will be 0. If x is equal to 1, we will retain that as it is, right? So now here I am considering the interval from 0 to 1. So this will be 0, this will be 0, this will be 0. That means till xn minus 1 all the values will be 0 and xn will be 1. Okay, so this is 0, this will be 1 and this is 0. So now you will be getting L of p comma f comma alpha as n minus 1 by n. Similarly, I have to find out L of p comma f comma alpha for partition 1 comma 2 and then for 2 comma 3. So again, what is my infimum value? F of it is, I have to consider this now because we are choosing the interval from 1 to 2, right? So 1 plus I minus 1 by n, you will be getting 1 plus I minus 1 by n itself. Again, what is delta alpha I? I will just write alpha of xi minus alpha of xi minus 1. Now substitute in your summation, you will be getting summation I is equal to 1 to n 1 plus I minus 1 by n into alpha of xi minus alpha of xi minus 1. Expand your summation, you will be getting 1 into alpha of x1 minus alpha of x0 plus 1 minus 1 plus 1 by n into alpha of x2 minus alpha of x1 plus 1 plus 2 by n into alpha of x3 minus alpha of x2. The process continues and at last you will be getting 1 plus n minus 1 by n into alpha of xn minus alpha of xn minus 1. Substitute the value of your alpha x. So you will be getting 1 into x1 minus x0 plus 1 plus 1 by n into x2 minus x1 plus 1 plus 2 by n into x3 minus x2 plus so on up to 1 plus n minus 1 by n into xn minus xn minus 1. Here my interval is 1 comma 2. So all the values till 1.999 you will be getting it as 1, then 2, that is till xn minus 1 it will be 1 and xn will be 2. This is 1, this is 1, this is 1, this is 1 and here it is 1, 1, this is 2 and xn minus 1 is 1. So since 1 minus 1 is 0, all this value will become 0. At last you will be getting 1 plus n minus 1 by n into 2 minus 1 is 1. So your L of p comma f comma alpha is equal to 1 plus n minus 1 by n for the interval 1 comma 2. Similarly, you can check for L of p comma f comma alpha, you will be getting 2 plus n minus 1 by n. Check this, you will get the result. You have to do what you are supposed to do is for mi, now this will be your value because we are considering the interval from 2 to 3, right? So now substitute this and expand your interval expand your summation. Since the interval is from 2 to 3 till xn minus 1, all the value will become 2 and xn will be 3. Substitute this value, you will be getting 2 plus n minus 1 by n. Now I have to add all these partitions LPF alpha, right? So L of p comma f comma alpha is equal to, for partition P1 we got n minus 1 by n, plus for partition P2 it is 1 plus n minus 1 by n, and for partition P3 it is 2 plus n minus 1 by n. So you will be getting 3 plus 3 into n minus 1 by n. I can do simplification further. So 3n into 1 minus 1 by n divided by n gets cancelled. You will be getting 3 plus 3 into 1 minus 1 by n. So I lower bound of f is equal to limit n tends to infinity L of p comma f comma alpha. That is nothing but limit n tends to infinity 3 plus 3 into 1 minus 1 by n. After substituting the limiting value, you will be getting 6. This is L of p comma f comma alpha. So now I have to do u of p comma f comma alpha for 3 intervals. Then I should add all this. Then I have to find out I upper bound of f, right? So in order to find out u of p comma f comma alpha, we need capital Mi. For the interval 0 comma 1, mi is nothing but f of xi, and it was I by n. I have already found that, right? You can observe here. So again substitute the values. This is summation I is equal to 1 to n I by n into alpha of xi minus alpha of xi minus 1. This will be 1 by n into alpha of x1 minus alpha of x0 plus it continues so on up to n by n is 1 into alpha of xn minus alpha of xn minus 1. So again, since the interval is from 0 to 1, all the values till xn minus 1 will be 0 and xn will be 1. That is 1 by n into x1 minus x0 plus so on up to 1 into xn minus xn minus 1, right? This is 0, this is 0, this is 0, intermediate terms all will be 0 and this is 1. So your up comma f comma alpha will be 1 for the partition 0 comma 1. Similarly we have to do for 1 comma 2. So that is u of p comma f comma alpha is equal to summation I is equal to 1 to n. Now you have to use this 1 plus I by n. So 1 plus I by n into alpha of xi minus alpha of xi minus 1, right? So this will be, after expand the limit, expand the summation, you will be getting 1 plus 1 by n into alpha of x1 minus alpha of x0 plus so on up to 1 plus, this will be n by n is, okay, you can write in this way. So alpha of xn minus alpha of xn minus 1. Substitute the value of alpha x, it is x1 minus x0 plus so on up to 1 plus 1 into xn minus xn minus 1. So again till xn minus 1 the value will be 1 and xn will be 2. So this is 1, this is 1 and this is 1, this will be 2. 2 minus 1 is 1. This all terms will be 0. You will be getting 2. 1 plus 1 is 2, 2 minus 1 is 1, 1 into 2 is 2. Similarly find out the last partition, that is for 2 comma 3. It will be, we will take this value now, that is 2 plus I by n. So it is 2 plus I by n into alpha of xi minus alpha of xi minus 1. Expand the summation and you will get the value as 3 here. Okay, so now what is the actual partition, that is overall partition? We have to add this and these two, right? That is 1 plus 2 plus 3, it is 6, and I can write this as I upper bound of f is equal to limit n tends to infinity u of p comma f comma alpha, that is equal to limit n tends to infinity 6. So answer is 6. Since lower bound of integral value and upper bound of integral value is equal, we can say that our function is Riemann-Stieltjes integral with respect to the function x on the interval 0, 3. This is how we solve this problem. Now let's move to the next topic, that is refinement of partitions. So as the name suggests, we are doing some modulations, some modifications with respect to the partition, right? So now I will define a new partition, say P star. This P star is a partition and I will call this partition P star as refinement of P. Initial partition is P and I want to say P star is a refinement of P if this P star contains P. I can represent that as P is subset of P star. That means P is contained in P star. P star is my new partition and in that new partition all the points of P is contained. For example, if P is equal to 1, 2, 3, 4, 5, then P star will be 1, 2, 3, 4, 5, 6. You can observe here all the points of P is contained in your P star. Along that we have extra point also. This is nothing but refinement of P. Every point of P is a point of P star, right? So I can write that as every point of P is a point of P star, or in other words I can say that P star refines P, or you can say P star is finer than P. A part of the points of P, P star may contain some other point also. So we say P star is finer than P. Or you can just say every point of P is a point of P star. That is nothing but P is contained in P star. Or I can say P star contains P. Okay, this is how we define refinement of partitions. So now using this concept, let us prove some of the properties in your Riemann-Stieltjes integral. Okay, the first theorem is we have two inequalities here. We are supposed to prove those two inequalities. As data, they have given that P star is a refinement of P, then we have to prove L of P star comma F comma alpha is greater than or equal to L of P comma F comma alpha. This is one inequality, and another inequality is U of P star comma F comma alpha is less than or equal to U of P comma F comma alpha. This is first inequality and this is second inequality. These two are one of the important inequalities. Okay. So now let's see how we can prove this. In order to prove this inequality, first what I will do is I will consider a partition P. Okay. P is nothing but if I have a closed interval a comma b, then I can define my partition as a is equal to x0, x1, x2, so on up to xn. This is nothing but my point B, right? This is a partition in the interval, that is closed interval a comma b. Now if I have a partition P star, suppose if I consider P star as another partition, it contains just one point more than P. That means along with these points, I have one extra point in my P star. I will denote that extra point as X star. And this X star will be lying in between Xi minus 1 and Xi. That means I can denote that as X star is my extra point which is in between Xi minus 1 and Xi. Okay. So now we know that what is this f? F is a bounded function for the entire interval, that is closed interval a comma b. Right? If function f is bounded over all the interval, then obviously it is bounded within sub-intervals also. That means if I choose this as my function f of x, if this function is bounded within this interval, then obviously this function is bounded within this interval also, or within this interval also. Alright, that means if a function is bounded in the entire interval, that implies you that the same function is bounded even in its every subintervals. So I can write that as, since f is bounded over the entire interval closed interval a comma b, this implies f is bounded on every subintervals. I will denote that subinterval as delta xi, where I is varying from 1 to so on up to n. Okay, so now I will define two infimums, say w1 and w2. Along with these two, we have one more infimum, that is mi. This w1 is a infimum with respect to the interval xi minus 1 comma x star. This w2 is an infimum with respect to the interval x star comma xi, and mi is an infimum with respect to the interval xi minus 1 comma xi. Okay, so these two are the infimums which we are defining along with mi. Since we have one more partition or one more extra point in our interval. Okay, now from this clearly I can say that w1 is greater than or equal to mi, because it is a infimum within this interval. So obviously this term will be less than or equal to w1 infimum, because this is for this interval. Right? Similarly, I can write w2 is greater than or equal to mi. Now, let us consider L of p star comma f comma alpha minus L of p comma f comma alpha. So we know what is L of p comma f comma alpha. It is summation I is equal to 1 to n mi delta alpha I. Since we are very clear with the intervals, this is a restricted intervals, that we are considering only one set of intervals, you need not to write this summation. You just write mi delta alpha I. Okay. So this p star is for two different intervals. So I can expand that as, we have seen that if we have two partitions, what we will do? We will find out LP comma F comma alpha for two different partitions. Then we will sum up those two. We have seen in the previous problem. In the similar way, I can write this as W1 into, this is for X star and Xi minus 1. So what is delta alpha I? It is alpha of Xi minus alpha of Xi minus 1. Here alpha of Xi is nothing but alpha of X star minus alpha of Xi minus 1 plus W2 into alpha of xi minus alpha of x star, because w2 is with respect to this interval, right? Similarly, minus L of p comma f comma alpha, we know what is L of p comma f comma alpha, just substitute that. So minus mi into alpha of xi minus alpha of xi minus 1. I can simplify this as w1 into alpha of x star minus w1 into alpha of xi minus 1 plus w2 of alpha of xi minus w2 of alpha of x star minus mi into alpha of xi minus into minus, it is plus mi into alpha of xi minus 1. Right. So now what I will do is, in order to make the simplification even more easier, I will just add and subtract mi alpha of x star to this equation. So this equation becomes w1 alpha of x star minus w1 alpha of xi minus 1 plus w2 alpha of xi minus w2 alpha of x star minus mi alpha of xi plus mi alpha of xi minus 1. Now I am adding and subtracting mi alpha of x star. Okay. So now I can take alpha of x star as common, so that I will be getting w1 minus mi. Similarly, if you take alpha of xi minus 1 as common, you will be getting w1 minus mi. Again, I can take alpha of xi as common, so we will be getting w2 minus mi, and we are left out with one more alpha star. So if I take alpha x star common, I will be getting w2 minus mi. Right. So now further we can simplify this as, in these two terms I can take w1 minus mi as common. We will be getting alpha of x star minus alpha of xi minus 1. Similarly, in these two I can take w2 minus mi as common. So we will be getting w2 minus mi into alpha of xi minus alpha of x star. So this whole thing will be greater than or equal to 0. Why? Because alpha of x is monotonically increasing function, right? And we know that w1 is greater than or equal to mi and w2 is greater than or equal to mi. So this whole term will be greater than or equal to 0. That means I can write my LHS part, that is L p star comma f comma alpha minus L of p comma f comma alpha. This whole thing is greater than or equal to 0, which is nothing but L of p star comma f comma alpha is greater than or equal to L of p comma f comma alpha. This is nothing but my inequality 1. In the similar way, we can prove for the second inequality. So what will happen in second inequality? The partitions, the divisions, everything will be same, but here you will not consider the infimums, you will consider the supremums. So in the same way, I will prove that w1, w2 and capital Mi will be the supremums, right? I can define this supremums for the interval. Again, you have 3 intervals here, that is w1 is for xi minus 1 comma x star, W2 is for x star comma xi, and mi is for xi minus 1 comma xi. Right? So since it is supremum, obviously your mi will be greater than or equal to W1, because mi is to the overall interval and W1 is in between points we have, right? So I can write this as W1 is less than or equal to mi, or we can write mi is greater than or equal to W1. Similarly, W2 is less than or equal to mi. Right? Now consider u of p star comma f comma alpha minus u of p comma f comma alpha. This will be equal to, substitute the values, so you will be getting, as we have seen in the inequality 1, the same procedure I have done here. The only difference is there I have added and subtracted infimum along with that alpha of x star. Here it is supremum, right? After that the same simplification again. So from this we know that W1 minus mi is less than or equal to 0, W2 minus mi is less than or equal to 0. So the whole thing will be less than or equal to 0, or you can write one more step as W1 minus mi into alpha of x star minus alpha of xi minus 1 plus W2 minus mi into alpha of xi minus alpha of x star. This whole thing will be less than or equal to 0, because W1 minus mi is less than or equal to 0 and W2 minus mi is also less than or equal to 0. So from that I can write the whole thing is less than or equal to 0. Now what was there in your LHS part? It was u of p star comma f comma alpha minus u of p comma f comma alpha. Now this whole thing is less than or equal to 0. From this I can conclude that u of p star comma f comma alpha is less than or equal to u of p comma f comma alpha. This is my second inequality. This is how we prove the properties on refinement. We have some more properties which will be discussed in the next session. Thank you.